Okay, back to the CPU. Remember we said in the CPU we have the control unit, we have arithmetic logic, and we have a whole bunch of registers. High-speed temporary storage. We also have the system bus that goes between memory and the CPU. And this is where the bottleneck is, because everything that we do has to travel across the system bus. So a couple things in particular. CPU, its job is to direct traffic. So it directs the instruction execution cycle. The control unit, as we mentioned as we went through the instruction execution cycle, interprets an opcode and directs execution of the instruction. The opcode is loaded into an instruction register and decoded to identify the operation. The CPU monitors the data transfer across the bus. In the AL unit is the computer's numeric calculator and logical analyzer. So it receives data from memory and registers, performs calculations, and stores results in memory if necessary. These internal registers, we will spend some more time on them later on. Most of the time, for a 32-bit machine, they're going to be 32-bit registers. If it's a 64-bit machine, they're going to be 64-bit registers. I say most of the time because we do have some registers that are smaller. Okay. Let me just highlight one thing real quick. I have the CPU, and memory. And we said we had the big fat data bus, but let's break it down. We kind of showed this before. I've got an address bus. The address bus holds addresses. It is 32 bits if it's a 32-bit machine. I've got a data bus. The data bus is bidirectional. The data bus can carry any data on it that we need. But we also have, now these are some of the buses that are part of the hierarchical construction of a system bus. But one I'll just mention to you also is the control bus. The control bus is what tells us, oh wait a minute, tells us who is using the system at what point. So because data and address buses are shared by all components, there must be a means of controlling their use, and that is what the control bus does. So it signals transmit both command and timing information between system modules, tells us if there's a bus error, an error condition, or perhaps even an address error, maybe an address went on the address bus that's larger or beyond what I can physically get to in memory, or could reset or send a signal that's a reset for the system. So the control bus kind of monitors all the transmission that's going on between the CPU and memory. All right, the address bus. 32-bit for our machine. For you guys, if you have 64-bit machines, just kind of go up from there, okay? This is important, though, because if the address bus is 32-bit, means we can address 2 to the 32, or about 4 gigabytes of data. That means if I have more than that in RAM, I can't use it. Oh, that's horrible. So 2 to the 32 is that. So for the unsigned range, this means I can start with byte 0 all the way to, 4294967 okay? So I can have that many bytes, each one that has its own unique address. Okay, data organization in memory. We've been talking about this, and I apologize, I probably should have brought it up before. When we talk about a byte, we are talking about 8 bits, where when I talk about the high order bit, or the least significant bit, or most significant bit, The high order bit, this would be low order or least significant bit. Okay? I can do the same thing with a word, which is twice or twice the size of a byte or 2 bytes. So it's 16 bits. And here I can still say, okay, I want the most significant bit or most significant byte, least significant bit or least significant byte. I also have a double word, which is 2 words or 4 bytes or 32 bits. And again, I can have most significant bit, most significant byte, most significant word, least significant bit, least significant byte, least significant word. I can get to all pieces of that. I can also get to a quad word which is 64 bits or 8 bytes. So that just kind of gives us a little bit of idea on terminology. Okay? All right. I think I'm going to do this in class just to get a little bit faster here. Let's talk about our registers. Okay, so many of these we've already talked about. These are all the different types. Let's go over them individually. The general purpose registers are 32 bits long. So 32 bits. I've got 4 general purpose registers, and they are EAX, EBX, ECX, and EDX. Okay, they are 32 bits. These are registers that are part of the CPU, so I can get to a lot of different parts of them. Let's use EBX, for example. The whole thing, all 32 bits, is EBX, but I can also get to the least significant word by calling it or just addressing BX. Within BX, I can also get to BL, which is the least significant byte, or BH, which is the most significant byte, low order, high order byte. Okay? That's the same for all of those 4 registers. I also have some index registers. Let's go back. We'll do these also in class. Index registers. I've got 2 of them that we're going to talk about right now. Then we'll talk about 2 kind of special purpose index registers. So the first one is ESI, or my source index register. I also have EDI, destination index register. Both of these are 32-bit. For both of these, I can get to, let's see, ESI, I can get to the low order word, but I can't get any more granularity. I can't get to the low order byte or high order byte of SI. What do these things do? Let me give you a couple of examples. So if I have a couple of instructions, then let's say I want to add sum to EAX. Whoa, sorry. So that makes it simpler. Add sum to EAX, where EAX is my destination. In this case, the address of sum is held in ESI because it's the source. Okay, so let's say I'm going to add EAX to sum, and in that case, the address of sum could be stored or would be stored in EDI. So just to tell you a little bit about how they work. 2 more index registers. Stack pointer is also known as, ESP. Base pointer is EBP. Okay? Stack pointer. Both of these are 32-bit. Wow, that's messy. 32-bit. The stack pointer moves as data is pushed or popped on the stack. So let's say here's our stack. I'm going to have a stack pointer. Maybe it's pointing way down here until I push something on the stack. Okay? So maybe then the stack pointer is going to be pointing always at the top of the stack. So stack pointer is always pointing at the top of the stack as data is pushed or popped from the runtime stack. We'll talk more about this later. Well, in fact, we'll talk more about both of these. The base pointer is used as a fixed reference point on this stack, so that as my stack pointer is moving up and down, I have a fixed reference. I use it when I'm passing parameters, for example. So a little bit about index registers. Let me just give you a quick example. Let's say for this, we want to do a couple of things. I want to add 5 to EDI. When I show or have an instruction in this form, okay, I'm going to add 5 to the contents of this register. So what's going to be in EDI afterwards? Let's see, EDI has this in it. Remember, it is a register, so it's in the CPU. I'm going to add 5 to it, so afterwards it's going to have 0, 0, 0, 0, 0, 5, 0, 5. Okay? In this case, and this is really the beauty of the index registers, when I put the square brackets around it, I am using EDI as a pointer to memory. So, in this case, let's assume that EAX is pointing at this address in memory. No, it has that value, I'm sorry. EDI will go back to EDI having this address. So EDI is pointing right here at the first byte, which would be that one. Okay? I want to add AX to what EDI is pointing at. In this case, this is going to tell me it's a 16-bit addition. So AX, the 16 bits of AX that I'm interested in are 00A2. What is the 16 bits that EDI is pointing at? Well, it's this. So let me tell you something really quick that we'll go into a lot more detail. Multi-byte scalar values stored in memory, where this is in memory, this is in the CPU, not memory, are stored in reverse byte order or little endian. Okay, so when I add these together, the addition is going to look like this. We do the math and I get 2 plus 15 is 17. That's going to be 26. 16 goes into that once with 10 left over. B and 3. I am, in this instruction, storing the results of the addition back in memory. So because multi-byte scalar values get stored in memory, this is going to overwrite memory in this way. I will have A1, 3B. Okay, don't sweat it. We'll talk more about that in class. All right, what else have we got? Segment registers. This is an example of something that's not 32-bit. These are 16-bit segment registers. The code segment, and remember, these segment registers go back to segmented memory model, where, remember we said the machine is going to partition memory into chunks or segments. Code segment is where we store code. Data segment is where we store data. These segment registers are extra data segments that were added as the architecture of this class of computer grew. Finally, I've got the stack segment for the runtime stack. So that's how I address them, CS, DS, etc. Okay, instruction pointer. Let's see real quick what I have. Oh, let's do that. That's good. The instruction pointer is also a 32-bit register called EIP. So again, 32-bit. It holds the address of the next instruction to be executed. Now, I kind of peeked ahead and let you see some of the things that we're going to be talking about because, again, this is critical in the instruction execution cycle, which is what we're going to be dealing with all semester. So let me talk about a couple of things. Earlier, used to be the case that we could pre-fetch instructions while I'm still executing the previous instruction. Now this is fetch only. I'm not going to try to implement both or execute both instructions at the same time. Prefetching was huge because the architecture of the machine itself hasn't really changed all that much. What has changed is how fast I can get to everything. How fast I can get to everything has changed because what I have done is said I can get to different parts of the CPU, different pieces, different components in different time slices. And in that way, in addition to prefetching, I can actually start execution of one instruction while I'm still executing the previous one. In fact, I can do this for multiple instructions. So let's say I've got my first instruction. Step one, I'm going to use, let's say we're using the bus. So I go across the bus, I pull this back and bring it to the control unit. Then I'm going to use the AL unit and then maybe a register. Okay? While instruction 1 is going in each one of these time slices, notice in time slice 2, I've already fetched instruction 2. That means in time slice 2, while instruction 1's using the control unit, step 1 can use the bus, and then can use the control unit, and then can go maybe back on the bus, and then maybe go to, well, let's not do the bus. Let's say we want to go to the AL unit. Where would we be going? Yeah, that'll work. And then maybe, again, back on the bus. Okay, so notice at each slice, different components are being used. So I can actually execute these. Now, in the third instruction, I want to go across the bus to get the next instruction. I can do that because step 2 is using a control unit, step 3 is using the arithmetic logic unit. Let's say my next step is I go across the bus. This is a simple addition between two registers, so I just want to use one of the registers. And I need to use EAX, but guess what? EAX is already being used by instruction 1. So I have what we call a stall in the pipeline, where instruction 3 just has to wait until the next time slice when the component it's looking for becomes available. Okay? All right. Let's call that one. Oh, there's my lovely picture. Ooh, that's even better. So guys, we'll pick this up with the next one, next recording.